Okay, so this is a video that explains the in relative motion in class assignment. A boat is traveling with a speed of 8 meters per second in still water and is going east, encountering a current traveling 3 meters per second going north. So the vector diagram situation will be something like this. The boat is traveling east. The velocity of the boat is east, and the velocity of the current is north. So the resultant velocity will be this one here. What is the resultant velocity of the boat? So then the magnitude of the resultant of the velocity will be the square root of 8 squared plus 3 squared. And in your calculator, so your calculator will give you 8.5 meters per second. And then the angle with the shore will be inverse tangent of 8 over 3. And this will be 69.4 degrees. So you can say that the resultant velocity as the observer sees it from the shore will be 8.5 meters per second at 69.4 degrees. You can say width of the shore, or you can say east of north. Now, for how much time does it take the boat to travel shore to shore? Then, knowing that the river is 150 meters wide, then we can say, since we are dealing with this direction, then we can say that the time to go from A to B is the same as time that will go from B to C, or is the same as the time that it goes from A to C, because those are independent uniform motion. So the easiest one to deal with is the distance from A to B over the velocity on this direction, which will be 150 meters over 8.0 meters per second. So then in your calculator will be 18.75 seconds. You can say that time to go from one shore to the other is 18.8 seconds. So for B, it is asking how much downstream is it going. So what they are asking actually is asking what is the distance between BC. So the distance, as we said here, now that we know the time, 18.8, we can say that the distance BC will be the speed on that, or velocity on that direction times time. So the velocity on that direction was 3.0 meters per second times 18.8 seconds, and this 3 times 18.8 in your calculator will be meters. So downstream is going 15.4 meters. Okay, the situation of this question is something like this. You have a river here. The current is traveling east, at 3 meters per second. And then the swimmer is able to swim at 14 meters per second in still water. What is the direction of the swimmer so that it ends up across to the other side of the river? So if it starts here, what we want is to end up here at point B. So the swimmer will start at point A and we want to end at point B. So the vector diagram will be something like this. The resultant velocity, we want it to end up straight to north. And then if we were adding the velocity of the current, we will do it on this way, since we are going with the opposite of that, because v of the current, and then the v of the swimmer, the velocity of the swimmer will be this way. Why are we writing it in this way? Because always we start with the resultant velocity is the velocity of the swimmer plus the velocity of the current. And from here, we'll find that the velocity of the swimmer will be the resultant velocity minus the velocity of the current. And on this relationship, we know the magnitude. We are looking for direction. We don't know the magnitude, but we know the direction. And for the current, we know both the magnitude and the direction. So now, since this is a 2D situation, what we will do is we will use components. When we use components, we do that in the same way as we do for every single vector. So we have vectors, horizontal component, vertical component. So we have the resultant component is here. The negative velocity of the current and the velocity of the swimmer. Since it is going straight north, then the velocity, the horizontal component of the resultant is equal to 0. And the vertical component is equal to the magnitude of the resultant. For the current, the horizontal is positive 3. Since we have the negative here, then will be positive, negative, positive 3. And then we don't know what is the horizontal component of the velocity of the swimmer, and we don't know what is the vertical component of the velocity of the swimmer. But from the horizontal component, what do we know is that x is equal to negative 3 meters per second, which means that the horizontal component of the swimmer is equal to negative 3 meters per second. And the vector diagrams tells us this, because now we know that the horizontal component of the swimmer is negative 3 meters per second. Since this weighs the shore as well, then we can find the angle alpha here. So the angle alpha will be the inverse tangent of no, not inverse tangent, will be inverse cosine, or will be inverse cosine of 3 over the velocity of the swimmer, that is 14, because we know the magnitude. And then in your calculator, 3 over 14 will be equals to 77.6 degrees. So you can say that the velocity of the swimmer will be 14 meters per second at 77.6 degrees. You can say north of west or with the shore. So this will be for the first part of the problem, and then when they are asking what is the resultant velocity, we can use the fact that the vertical component here is equal to y equals to the resultant. But what y was actually the vertical component of the swimmer's velocity, which if we refer to the vector diagram here, will be this vector here. So this is the vertical component of the swimmer's velocity. And it is whatever is the velocity of the swimmer, 14 times sine of the angle that we just found. 0.6 degrees. So 14 times sine 77.6. The resultant velocity will be 13.7 meters per second going north. And then the last part of the problem is asking you, supposing that, let me see it again, supposing that the river is 230 meters wide, how much time does it take the swimmer to travel shore to shore? So if we bring the river again here, the river is here, and this is the resultant. This is the current, and this is the swimmer. But if you go from A to B, then you will take this distance, 230 meters. Then you will take this distance and divide it by the velocity on that direction, that is the resultant velocity. So if you're finding the time from A to B, is the same as saying that is the distance from A to B over the velocity on that direction, which is 230 over the resultant velocity. And that resultant velocity, we just found it, is 13.7, not 17, 13.7 meters per second. So in your calculator, 230 divided by 13.7 will be 16.8 seconds. And this concludes the second question. Okay, so what do we have on this case is a plane that is traveling at 50 degrees north of west at 400 kilometers per hour, and then it's experiencing a wind with a magnitude of 85 kilometers per hour at 35 degrees south of west. We always start with the resultant velocity is equal to velocity of the plane plus velocity of the wind. Since this is a 2D situation, what we do is we use components. And when we use components as every other single vector that we have seen even prior to this. So in this situation, we have the velocity of the plane that is between north and west at 50 degrees with west. And then we have the velocity of the wind that is between south and east. And it is 85 kilometers per hour. So this is 85 kilometers per hour. And this angle here is 35 degrees. So the magnitude of this is 400 kilometers per hour. So now we build the table of components. So we have the horizontal component here and the vertical component here, the velocity of the plane, the velocity of the wind, and then we have the resultant velocity. So we build the right angle triangle that includes the given angle, and the horizontal component of the plane is this one here. So the horizontal component will be 400 times cosine 50, and it is negative, so negative 257.1. And the vertical component is 400 times sine 50, and it is positive, so positive 306.4. And for the velocity of the wind, this will be the horizontal component, and this will be the vertical component. So the horizontal component will be 85 times cosine 35 degrees, and it is positive, so it's positive 69.6, and the vertical component will be 85 times sine 35, and it is negative, so it's negative 48.8. We add the two components together, so negative 257.1 plus 69.6 will be negative 187.5 for the horizontal component of the resultant velocity, and 306.4 minus 48.8 will be positive 257.6. What does that mean? Is that the horizontal component is negative 187.5, and the vertical component is positive 257.6. So we construct the rectangle, and the diagonal that starts at the same starting point is the resultant velocity. The magnitude of the resultant will be the square root of 187.5 squared plus 257.6 squared, and 187.5 squared plus 257.6 squared, the whole thing square root, will be 318.6 kilometers per hour, And then you have the liberty to choose the angle. I'm choosing angle alpha, which is the inverse tangent of 257.6 over 187.5. So inverse tangent of 257.6 over 187.5 is 53.95. You can easily say 54 degrees. So then you write that the resultant velocity of the plane that is traveling 400 kilometers per hour in the direction 50 north of east and is experiencing a wind with a velocity of 85 kilometers per hour, 35 degrees south of east, will be 318.6 kilometers per hour at 54 degrees, and this is north of west. Okay, so this is the last question. A plane is flying in still air at 370 kilometers per hour, and it is aiming to reach a city that is 560 kilometers west. So it is starting at CDA, and then CDB is straight west at 560 kilometers. During this flight, it is experiencing a wind that is 90 kilometers per hour at 40 degrees south of west, which is vectorially is a vector that is with a magnitude of 90, and angle here is 40 degrees with the west, between south and west. What is the adjustment in the direction that the plane have to make to reach its destination? So what it is telling here is that the resultant velocity has to be west. The resultant velocity has to be west. We always start with the relationship that the resultant velocity is the velocity of the plane plus the velocity of the wind. From here, we find that the velocity of the plane will be the resultant minus the velocity of the wind. If we were going with the velocity of the wind, then we will go somewhere on this direction. Since we are going with the opposite of the wind, then we will go on the opposite direction. So this is the negative velocity of the wind, which will tell us that the resultant velocity is a vector that starts at the starting point and end at the end point. So this is the adjustment that the plane has to make in order to reach the destination straight west. On this relationship, what do we know is that the magnitude is 370, but we don't know the direction. We don't know the magnitude, but we know the direction. And for the wind, we know both. However, since this is a 2D situation, what we do is we still use components. And in order to use components, we construct a table. The horizontal component, vertical component, and then here we have the resultant velocity, negative velocity of the wind, and velocity of the plane. So since there's a 2D component, 2D, we use components. This is the table of components, and then for the velocity of the plane, the horizontal is X, the vertical is Y. It's exactly the same as we have done it before in class. So now, from the horizontal component, what we have is a negative VR plus 68.9 is equal to x, which actually is the horizontal component of the velocity of the plane. And from the vertical component, we have that y is equal to, or we can say that positive 57.9 is equal to y, which actually is the vertical component of the velocity of the plane. So now, the vertical component, if we bring the plane velocity of the plane, the vertical component is this one here. Okay. Which if we consider the angle alpha is the opposite of angle alpha, and the magnitude of this plane of this velocity was 370 kilometers per hour. So in order to find the angle alpha, we will use inverse sine of 57.9 over 370. And in your calculator, you will find that it is 9.0 degrees. So you can say that the plane has to adjust to make a 9-degree angle with the west axis, or you can say that the velocity of the plane should be 370 kilometers per hour at 9 degrees north of west. So now the magnitude of the resultant velocity will be found by using the relationship that we get from the horizontal component. So it is negative VR plus 68.9 is equal to the 370 times, we are looking for, it's negative because it is going in this direction, 370 times cosine 9 degrees. So 370 times cosine 9 is equal to 365.4. So from here, we find that it's negative. The resultant velocity will be using your 434.3 kilometers per hour. And if we are looking for, so you can, if you write it as a vector, then it will be west or negative. The calculations here will tell you that it is negative. And if you are looking for the time that it needs to go from city A to city B, then you will take the distance between those two cities, that is 560 kilometers over the resultant, which is on the same direction, kilometers per hour. So 560 divided by 434.3 will be 1 hour, 1.3 hours. So this is the total time, and this is the velocity.